Hi, this is a short lecture in the context of modeling biomedical processes, specifically heat and mass transfer in biomedical processes. It introduces some example formulations of the source terms in a diffusion equation. So just like in the heat equation, we have a term, a source term that is separate from transient or flow or conduction. It seems to represent just thermal energy appearing somehow. But of course, energy doesn't just appear, it is a conversion from some other form of energy. In a very analogous way, in the mass diffusion equation, we have a mass source term. Now, here the term represents the amount of this mass species. So A is my species, amount of this species that appear or seem to appear from nowhere. Of course, it's not possible to appear from nowhere. It represents conversion of other mass quantities into this mass species or vice versa. So typically, this is through a reaction. So this is the mass source term that we would be spending some time how to formulate it so that we can solve the mass transfer equation. So one of the simplest common situation is the zeroth order reaction. So we write, and you must have written this before, a zeroth order reaction when the quantity is being depleted is minus Kc times 0. So this equation, when we write it for the reaction, we kind of implicitly assume that there is no flow of the mass and there is no diffusion. So it's just the reaction part that we write here. And in terms of the units, then, if C normally is in moles per meter cube per second, so then this, C would be just moles per meter cube. And so this would be minus K. So its units would be moles per meter cube per second. Okay. So in the mass source term, what we write is this. Okay. So this will go into the mass source term. Now, if this rate constant is temperature dependent, and again the most common temperature dependency is Arrhenius temperature dependency, so then K can be written as K0 e raised to minus. So the source term, this is my mass source, would simply be equal to this quantity. Okay, and that will get plugged into here. Another one that's even more common generally is a first order kinetics. So here we write the equation as dc dt is equal to minus k times c to the 1. And again, the unit for this term, this whole term, is still going to be this moles per meter cube per second. Okay, because concentration is in moles per meter cube. Okay, so then it is this that is my source term. So this Ra, the mass source, is equal to minus K times Ca. Now again, if this K is temperature dependent, then that's equal to K0 times E raised to minus E over RT by Arrhenius temperature dependency. And so the mass source again would be written for the first order reaction as this. So this will get substituted in the mass source term. So this one is for first order, and then this one is for 0th order. While the previous slides are sufficient to do the calculations, we're going to see an example of what is a 0th order reaction, and we are going to also see how we can estimate quantities like K0 and E over R. If you see in the previous slide that we need to calculate the mass source term. So we're going to do this for thermal injury. So almost 75 years ago, a researcher conducted experiments on temperature time combinations that gave the same level of burn injury, or damage. And this is how the data looks. So at a certain temperature, and this time it gives, let's say, a necrosis. Okay, now the which is a 3rd degree burn. Okay, so the same burn can happen at a higher temperature and shorter time, which makes sense conceptually. So we can have many temperature time combinations. We can have many temperature time combinations for the same injury, leading to this iso injury curve. So this is for, let's say, necrosis. Okay, iso injury curve. Once we have data, we can try to fit. And before that, let me also show that for the same temperature, if we heat it for a lower time, then we get a lower level of injury. And at this lower level, again, you can have a number of combinations that give the same injury. So this injury is basically pain threshold. So it's a much lower level of injury. So once we have this data, we can fit a line. We can fit a line and get this line so that we can operate, we can interpolate in between or extrapolate and so on. So for this, we think of the injury as a 0th order reaction that is temperature dependent. So modeled as a 0th order reaction, this is my injury, and this was already shown as the expression for 0th order reaction. This is like our K in the past, and so this is like K0. Okay, and there is sort of omega raised to the power 0, which is 1. So which is why omega is missing on this side. It's a 0th order reaction that increases. So there's a positive sign here. There's a positive sign. So injury increases with time. Now, if I integrate this, I write omega is equal to a e raised to minus e over RT times t plus omega 0. And so since we do not have any initial injury, so no initial injury, then we get this expression for injury as a function of time. If we fit this equation to the experimental data, because we already have temperature time combinations for the same injury, that's here, this one, and if we fit there, then we get to estimate a, e over r, and omega values for a certain type of injury. And so if we do that, we get omega equal to 0.53 for the injury threshold. So this one corresponds to omega equals 0.53, whereas omega is 1 for the complete necrosis. Okay, so once we have these values, then I can calculate injury at any time for any temperature. That's what our purpose is. So again, injury, once we have these values, injury kind of starts from 0 and increases. So when it reaches 0.53, we call it reach the injury threshold, and when it reaches 1, it's the complete necrosis. So how do we do these calculations? We'll see in the next few minutes. The 0th order equation that we just derived has an important application in thermal cancer therapy. So the cancer literature has the equation that the cumulative equivalent minutes in cancer therapy is given by this equation that we will explain in a second. It uses 43 degrees as the reference temperature. And what this equation says is that if you heated something at temperature, if you heated a tissue at temperature T for time T minutes, the amount of thermal destruction in the tissue, the thermal injury of the tissue because of heating for T minutes at temperature T is equivalent to heating for T43 minutes. So T43 is a symbol, T43 minutes at 43. So again, repeating, if you heat something at temperature T for T minutes, this equation says that is equivalent to heating at 43 degrees for T43 minutes. So this table shows the time in minutes needed to reach necrosis for different types of tissue. And so back to this curve, what this equation means is if I needed to reach, let's say at T43, I needed to reach some 240 minutes here, okay. This equation says that if you do this at a higher temperature, you are going to then need some other time. So let's say 1 minute. So that is the meaning of this. Or another way to look at is, if you heated something for 50 at 52 for 1 minute, it is equivalent to heating at 43 for 240 minutes. We will see that this equation can be derived from zeroth order kinetics. So recall, zeroth order kinetics is written as d omega dt is equal to some constant, zeroth order kinetics constant, if you'd like, omega to the 0 is equal to k. And so let's write that in terms of the temperature dependency as a e raised to minus e over RT. This is my zeroth order reaction, and from this we're going to derive this equation. Okay, and so omega, then from this equation, omega would be integrating the part when temperature could be changing with time. So it's the integral of this term. Now we are saying that the amount of injury for this would be equivalent to some other amount of heating, some other duration of heating, T43, at 43 degrees. In other words, 43 degree at 43 degrees for T43 minutes would give me the same injury as this. So these two are equivalent. So they are equivalent. Okay. And so when it's 43 degrees, of course, if T is 43, it's a constant, so we can take it out. So we can do the integration, and so we get T 43 here. So now solving for T43 from the above equation, it goes like this. So integral 0 to T a e raised to minus e over r times T plus 273, okay, dt is equal to let's say a times T43, and this other part I'm going to divide now. Okay, so e raised to minus e over r 43 plus 273. Okay, and this a cancels, and I can write, because this thing is a constant, I can take it inside the integration. And so I can write 0 to T e raised to minus e over r T plus 273, okay, minus e over r times 43 plus 273, okay, dt is equal to T43. Okay, so we're trying to find T43, so we're going to simplify this part, And so now it's I take minus E over R factored out, and so we can write this, and so that, let me clean up these parts here, and so that is equal to minus E over R times, I carry out this subtraction. So T plus 273 times 43 plus 273 minus, and so 273 cancels out, and I get T43 is equal to, yeah, sorry about the messy part, but it's T43 is equal to E raised to minus E over R 43 minus T divided by T plus 273 squared dt. So we have an expression for T43. You see, this is supposed to be the same, but it's not. It doesn't look the same. Okay, so we still need to do some additional simplifications, and that's what will be in the next slide. So this is the one that we just derived, and if we continue the derivation, you notice that if the temperature is constant, meaning the heating at the other temperature T for time T, it's at a fixed temperature. It's not 43, it's at a different temperature, but at a fixed temperature. So if that can be taken out, this part can be taken out of the integral, like here, and so it'll be multiplied by the time, and now I can rewrite this part as here. As you can see, I just simply rewrote, and that can be further rewritten as here. So when I'm writing it this way with 43 minus T as an exponent, I'm sort of doing this. E raised to x times y is same as e raised to x raised to the power y. So I'm just doing that. So it's this guy times the rest, and I kept that part, the first part, and the other part I put it at as an exponent. And now we call this part as R. So that leads to my equation as T43 equal to R raised to the 43 minus T times T, which is what we wanted to show. So to repeat, this equation gives the equivalent minutes at 43. How many minutes is this injury equivalent to at 43 minutes when your actual heating is at temperature T and time T? Now this R is equal to E raised to minus E over R over T plus 273 squared. So you can approximate R as E raised to minus E over R over even 43, for example. Okay, you can approximate R this way. So that is how you get R. So now we talk just a little bit about implementation of this calculation in a software. Again, when the temperature is varying, then this equivalent heating time, so this we keep referring to this as the equivalent heating time at 43 degrees for an actual heating that could even change with time, where the temperature could be changing with time. And so if I want to implement this in a software, meaning for some temperature time history, I want to calculate what is the final T43 time, what is the equivalent heating time, what is the time that will give the same injury if it were heated at 43 degrees. Okay, so instead of the integral form, we can think of, see, this is equal to something integral dt. We can think of it as the differential form. dt43 dt, dt43 dt is equal to this. And so instead of this, we want to implement this version. And so that can be done very easily in any software. If the software has an ODE solver, as for example in COMSOL, the ODE solver can directly just implement a simple ordinary differential equation like that. Or if it has a species equation solver, so let's write the species equation in 1D. So del C del T plus U del C del X is equal to D del square C del X square plus RA, right? And so this is the species A. Okay, so this is my normal species equation. If a solver is there for this equation, then all I have to do is set u equal to 0, so that drops out this term. Set d equal to 0, so set u equal to 0, d equal to 0, so those two terms drop out. Now my Ca concentration is this T43. So you notice the left hand side is equal to the left hand side here, and the right hand side is all that, minus e to the minus e over r, 1 over t plus 273 minus 43 plus 273. Okay, and so then you can fool the species equation and make it solve this equation that you want. So then that will give me this equivalent heating time at any location in the tissue and at any time.